right, now there's also some funky things that we can do with the gradient. So instead of acquiring a bunch of these little square pulses, we could play out something like this. So these are actually, one is a sine function as a function of time, the other one's a cosine function. So they're 90 degrees out of phase with each other, and they play out. Now remember, this is equation number 3. So what would this actually look like in a k-space trajectory? Well, it's a spiral. So it looks something like that. And so basically by acquiring a spiral-based readout, first of all, you're not acquiring all of the k-space, but you're effectively imaging with a 0 echo time. So if you're trying to image something dynamically, then you're basically getting the maximum amount of signal at the very beginning before anything really starts to dephase. And some of the arterial spin labeling that is run at the Seaman Family MR Research Center is based on this spiral readout. Now, one of the disadvantages is obviously you can't just do a normal 2D inverse Fourier transform to get your image. You have to either do some sort of fancy reconstruction, or you have to regrid your data as you sample it onto a 2D grid, and if you've got any inhomogeneities, that can cause some blurring. But the basic principle is that we're trying to basically speed up the acquisition. So you can think about this kind of as spiral EPI in some respects. Okay? Now, there is something called fast spin echo. So we've talked about some of the more gradient echo-based speed-ups. And so for any of you that are using HASTE, the HASTE is a type of fast spin echo, and it kind of works like EPI in that between your 90-degree pulses, you're acquiring more than one line of k-space. And so basically you apply this 90-degree pulse, tip your transverse magnetization, and then you apply successive 180-degree pulses. And so now your decay is more based on T2 instead of T2 star, so you're going to have more image contrast compared to some of those gradient echo based. Now, if you notice these weird sort of castle-looking pulses here in the slice selection, that's really just a slight dephasing and then rephasing again, lobe attached to this 180-degree pulse that we talked about before. Okay? And so, like I said, an example of this is HASTE, which some of you may be using. So the other thing you'll notice is that there's no phase encoding gradient here. It's all the phase encoding and rewinder gradients in GY are in between these pulses, and this is why. Because when we talk about this k-space trajectory, so we initially dephase everything in the positive direction. So we move over to this edge of k-space, then we apply our 180-degree pulse. We apply this little lobe here that actually moves us down in k-space. Then we do our readout, and then we move back to the center of k-space. The next 180-degree pulse happens here and moves us back. So basically we're always acquiring our lines in the same direction because of those 180-degree pulses. And basically what we're going to do is build up the same k-space, except that we're not zigzagging back and forth while we're actually doing the acquisition. The 180-degree pulses that we're applying in between are actually moving us back to the left-hand side of our k-space here. And again, this is another example where you have this idea of the effective echo time is when you collect your center lines of k-space, and then your TR is the amount of time between your 90-degree pulses. Okay? And the reason that we have it off center like this, again, is so that we still have the maximum amount of contrast when we cross the center of k-space. Okay? All right, so those are some of the pulse sequence ways that we can acquire more k-space per unit time. Okay, and so now we're going to move on to the next concept, which is what happens if we can skip lines, so we don't actually have to acquire as much k-space. So let's say we skip every other line. Well, what does that look like? So basically, all I did was I took this k-space and zeroed out every other line. Okay. So what does the corresponding image look like? It looks something like that. Why does it look like that? Well, if you remember our discussion a few talks ago, remember there's this reciprocal relationship between points in K-space and points in image space. And so remember, we know that the spacing in the y direction between our K-space points is inversely proportional to the field of view in the y direction. And similarly, the field of view in the x direction is inversely related to the spacing between our points in Kx. Okay? So what happens is, if we skip lines, we're now doubling the space between our adjacent K-space points in the ky direction. What that means is that we're halving the field of view in the y direction. So we're still acquiring full readout points in this direction, but we're undersampling in this direction, so it looks something like this. And then if we skip even more lines, yes, we're acquiring the data faster because we're not acquiring as many lines, but when we do our inverse Fourier transform, the image starts wrapping on itself like this. Okay? So this brings us to the fundamental basis of parallel imaging. And I'll read off some of the vendor names over the next couple of slides, because each one does it a little bit differently, because they have to make their patent money as much as possible when they sell you their scanners. So the basic idea is, remember, we have these multiple green RF coils that we're using in the magnet. In this case, we're talking about receiver coils. And so what we do with parallel imaging is we undersample the K-space by skipping lines, and then we use the coil position information to reconstruct full images. And so you have to think about the fact that each one of these coils is acquiring its own image that is going to be weighted by where it is positioned with respect to, in this case, the brain. So you know that if the coil is over here, it's going to have a pretty weak signal for the tissue that's over here, and vice versa. Okay? And so GE uses something called SENSE, which is called sensitivity encoding, and this is by Klaus Prusman. And so basically what you do is you skip every other line of K-space, and you still have these 4 coils that are positioned where you know, and so you're going to get 4 different aliased images. And if you look at these aliased images, you can even see that this particular coil configuration, let me just go back and show you that again. Like this wrapping that we're seeing is actually not a problem for this particular coil configuration because of where the coils are located and the direction of that wrap. And so basically how SENSE works is it takes these 4 images from the 4 coils, and it takes the coil sensitivity information and basically applies a basic matrix unwrapping to unwrap the full image. And so that's how SENSE works. Okay? Now there's something for you Siemens people called GRAPPA, and this is by Mark Griswold's baby. And basically the idea is it's similar but different. So we still have our undersampled image, and we've got these. We still have these coils like this. So basically what we do is we fully acquire, like, let's say, the central 12 lines, and then we undersample every other image in K-space. And basically, remember, the center of K-space is sort of our bulk contrast. That's basically weighted by the coil sensitivity profile. And so what we do with GRAPPA is we basically take an average of everything in these little boxes to basically fully reconstruct this full K-space to get our full image. So in this case, you don't actually need to acquire the coil sensitivity profile, but you need to make sure that you're acquiring some reference data at the middle that is fully sampled. Okay? And so that's the main difference between SENSE and GRAPPA. So SENSE is image-based reconstruction that requires acquiring a coil sensitivity profile, and GRAPPA is K-space based that requires acquiring a full center of K-space with these lines, and then undersampling the edges. Okay? And so that's the essence of parallel imaging. And so what if we can we save time by zero padding? So instead of skipping lines, what if we only acquire this central stuff? Well, what does that actually look like? Well, it's going to give us an image that looks something like this. And this one doesn't actually look too bad, but when I undersample it even more, you can see that we can start to get some of these weird sort of ringing, aliasing artifacts. And if you remember from last time, remember if you have a sharp edge in one domain, it's going to cause ripples in the other domain. And in this case, we're causing a sharp edge in our K-space acquisition, which is causing these ripples in our image domain. And the sharper that cutoff is, the more apparent those ripples are going to be. And so again, this is called Gibbs ringing artifact. So if we look at something like this, we get a lot of ringing artifact in the image. So we're acquiring the images faster, but now we're introducing this ringing artifact. And so some of the things we can do to reduce that edge effect is, instead of having this boxcar sampling of K-space where we just put zeros out here and then have this sharp edge, we could apply a filter. In this case, this is just an example of a Hanning function. So basically it's 0 out here, and then it goes to 1 here, and then goes back to 0 here. So it gives us, instead of sharp edges, it gives us a smoothing function. So if we think about acquiring only half of the lines like this, we get some ringing. And then if we apply this filter, which is actually coming out of the screen at you like this, then we can reduce the amount of ringing. The problem is that it can introduce blurring. And so if we look at this one that has a lot of ringing and we apply that Hanning filter, we've gotten rid of the ringing, but we've added a lot of blurring. Okay? And so these are just some of the techniques that we can use to increase the temporal footprint of our acquisition, depending on what we're trying to do. All right, so let's just quickly summarize here before we run out of time. So the first thing that we talked about, well, we talked about spectroscopy a little bit, but we talked about this idea that if we want a finite slice, we have to change our boxcar RF function to this sync function, which again, in the frequency domain is a boxcar. And we talked about this rephasing lobe that we have to put here in order to rephase the spins. And we talked about both spin echo and gradient echo methods for acquiring 2D K-space. And so the rest of the time was spent talking about ways that we could increase the amount of, or basically decrease the amount of time it takes for us to acquire an image, which allows us to either get more images or faster images or image transient phenomenon like heartbeats, that sort of thing. And so we talked about the fact that for parallel imaging, what we do is we use the coil sensitivity profiles to allow us to undersample the K-space and fully reconstruct the image. And then we also talked a little bit just briefly about how if we do zero padding, then we have to apply some sort of filter to get rid of some of that Gibbs ringing. Okay? And so that brings us to the end of part 5. So we're actually going to start part 6 with a full recap instead of doing the recap at the very end. And then the second half of the talk next time is going to talk about some more advanced strategies like weighted imaging, different angiographic techniques that are more specific to whatever physiology you're actually trying to measure. Today I tried to be a little more vague in terms of the actual pulse sequences that we were talking about, and what we're going to talk about next time is the actual implementation of some of those strategies. So I want to acknowledge the MNI Atlas that I used for the simulations for this talk, and thank you for your attention. Are there any questions?